Hello friends, welcome to Risingpearl.com. Today we are talking about Series 5 where we are learning a great deal on polynomials. This is going to be our fourth webisode and today's topic friends is the geometric representation of a linear polynomial. So let's get started. Now in the first webisode, that is when we started the series, we talked about what is a polynomial, degrees of polynomial, linear, quadratic, cubic polynomials. So we saw that we represent a polynomial by px. P stands for polynomial. Within brackets we write x, which is the variable. So polynomial in which variable, and let's say, and this is an example of a linear polynomial. This is a polynomial in variable x and the degree is 1. So this is a linear polynomial. Similarly, we can actually write a quadratic polynomial. Let's write a quadratic polynomial. So quadratic polynomial has a degree 2. That is a polynomial where the degree of the polynomial is 2, like in this case 5x squared minus 2x plus 10. Here the degree of the polynomial is 2, so this is a quadratic polynomial. And similarly, let's write a cubic polynomial. Cubic polynomials are polynomials that have a degree 3. So this simply is a cubic polynomial. Because the focus for us in this webisode is that the graphical representation, we will use the next few episodes to go through each one of these types of polynomial. So for this webisode we are going to focus on the linear, the geometrical or graphical representation of linear polynomial, and in the next few episodes we will take up the same thing for quadratic and cubic polynomials. So friends, here I have written a linear polynomial px equals 2x plus 6. Now what we are going to do is, because we are looking to represent the or find out the graphical representation of a linear polynomial, we have to draw graphs, and we know from our earlier grades that whenever we draw graphs we use coordinate geometry. We use x-axis, y-axis. We use the coordinate planes to plot the points on the graph, and then we join them and draw the graph. So here, so px is equal to 2x plus 6. So what we are going to say is that this px, we are going to assume this is y. So you have x is your x-axis. This is that x. And the value of the polynomial at each of the different values of x is going to be y. That means the value of the polynomial, like we saw in our second webisode, I think it was, that is the value of polynomial at each and every of the value of x, we will call it y. So like we had seen earlier, we are going to first make ourselves a grid like this. So the top row will be values for x, and the bottom row will be values for y, or the value of the polynomial at each of these values for x. Now we will want to have at least 3 unique values of x, and we will talk about that, and it will become clear why as we move along in this webisode. So how can we take any values of x? So the only criteria that you would want to keep in mind is that you do not want to take such a value of x that will in turn make the value of y, or the value of the polynomial for that value of x, as a fraction or a decimal number. So you would want to make sure that both x and y are whole numbers. Why do you want to do that? Only because you want to make sure that you have whole numbers. It will be easier to draw them, to locate those points on the graph and to draw your graph. So it is much easier to have 3 or 5 rather than having 2.33 or something like that. So for right now, so we are going to take, let's say x equals minus 4, then we will take x equals minus 2, then we will take x equals 0. We could have taken more points, and you can really, I have randomly picked 3 values, and you will just get to know this in a moment why I have picked these values. You could have literally picked any value that you choose. Now for each one of these values, you need to find out the value for the polynomial at, for example, x equals minus 4, at x equals minus 2, and 0. So let's do this here. So the value of the polynomial at minus 4 will be equal to 2 times x, so x is minus 4 here, plus 6. So you will have so you have 2 times minus 4 is minus 8 plus 6, or this will be minus 2. So we put minus 2 here. That is, for x equals minus 4, the value of polynomial is minus 2. Similarly, let's do it here, for x equals minus 2. For x equals minus 2, the value of the polynomial is 2 times x, which is minus 2, plus 6, or you get minus 4 plus 6. So 6 minus 4 is 2. So you get the value 2. And then if you take x0, if you take x0, this is one of my favorite values, because if you take x0, then this whole term becomes 0, so y equals 6. So it is just easier because you have to find out each one of these values one by one. So if you take simply 0, then one term becomes 0. It is just easier to quickly find out the value of the polynomial. Now, next step is we have to draw the graph, right? So what we have done so far is we have found out the coordinates, right? So if you think about this, so we have actually found out 3 points. So this one is x4, y minus 2. So again, recall that in coordinate geometry, we actually, each point is represented by 2 coordinates, right? X and y. So this point will be minus 4, minus 2. The second point will be, first we write the x, which is minus 2 at the top, and then we write the value for the y coordinate 2, and lastly x is 0 and y is 6. So the next step is for us to draw a coordinate plane. Now when we draw the coordinate plane, what we would want to do now is that we would want to get a table. Let's quickly get a table in here, and now let's write those values. So we have x as minus 4, then we looked at x as minus 2, then we looked at x as 0. So for y minus 4, so x minus 4, the value of y was minus 2. For x minus 2, the value of y was 2, and x0, this one was 6, which we just calculated earlier. Now we would want to plot each of these points. So the first point, and here we have a x-axis, so x dash, y dash, and this is our origin, right? So the first point is x is minus 4, so 1, 2, 3, 4 on the left side of origin, and y is also minus 2, so 1, 2. So from here 1, 2. So this point is minus 4, minus 2, right? The next point is minus 2 and 2. So x is minus 2 again, so 1, 2, so minus 2, but y is plus 2. So we go up 1, 2. So this is the second point, which is minus 2 and 2. And similarly, the third point that we have actually found out is x is 0. That means this will be on the y-axis, and y is 6. 1, 2, 3, 4, 5, 6. Let me circle this so you can actually see where the point is. So we have actually found out 3 points. Now the only thing left is for us to draw a curve or draw the graph which connects each of these 3 points. So you will see that we can simply draw a straight line like this, which can connect all the 3 points. So 1, 2, and 3. In other words, so the first thing is why I pick these values is because I have actually done this before, and so I have picked these points earlier, right? So I knew what value I want for x. So in order to make sure that I get a nice clean straight line, I actually have picked these values. But like I said, you could have really picked any value that you choose and then find out the corresponding values for y, and then find out whatever the graph that you get. So in this case, so for px, let's write it here, for px, which was equal to 2x plus 6, this was our polynomial, linear polynomial. We drew the graph and we found a straight line. That means the graphical representation of this polynomial, this linear polynomial, is a straight line as shown in this figure, in this diagram. So the next step what we are going to do is we are going to now find out, let's try one more and see what happens. So here I have given myself another linear polynomial, but this time I've gone a little bit different, right? So here what we have done, so our polynomial right now is minus 3 by 5x plus 6. Again, we are going to assume that the value of the polynomial is y, so y equals px, which is equals minus 3 by 5x plus 6. Again, please note that the last polynomial, last example, and this one, these are just random polynomials, linear polynomials. I'm just writing, you can take literally any linear polynomial and whatever we are discussing will be true for that. So these are just two random polynomials that I have taken. So in this case, again, we are going to do the same thing. So first thing is we are going to draw the grid, our small table, and we want to put three values here. So now if you look at why I have taken this particular example, is that here the coefficient of x is minus 3 by 5. So remember, like what we discussed earlier, we want to make sure that the value of y is a whole number. We are looking to get both for x and y, we are trying to get whole numbers, so it's easier to plot those graphs, right? So here, in order for me to have whole numbers, I need x to be a multiple of 5. That is, x should be a multiple of 5, like 5 times k, where k equals 1, 2, 3, etc. It could be also minus 1, minus 2, minus 3. So k equals this. Why? Because if k equals this, 5 times this, then I can actually divide that by 5, right? So if I take x equals 5 times k, then x by 5 will basically be a whole number, right? So if I take, for example, 10, so let's take some values. So let's take x equals, let's say x equals 5. So why don't we start with x equals 5? If we take x equals 5, going with, like, x is a multiple of 5, so p5 should be equal to, so here we have minus 3 by 5 times x, which is 5, plus 6, right? Or 5 and 5 will cancel out. We will have minus 3 plus 6, or this will be 6 minus 3, which will be 3. Similarly, now let's take x equals 10. So the next multiple we are taking, so we took x equals 5, let's take x equals 10. So let's write it here. So the value of the polynomial at x equals 10 is minus 3 by 5 times 10 plus 6. So here what we have is, so 5 1s are 5, 5 2s are 10. So minus 3 times 2 is minus 6. So minus 6 plus 6 is, they cancel out, it is 0. So here for x equals 10, we are getting the value of the polynomial is 0. So again, see that if I would have just simply taken x equals 1 or 2 or 3, I would have gotten into a fraction, right, which we are trying to avoid. So by taking x as a multiple of 5, we are making this first term a whole number, and a whole number plus 6 will be always a whole number. So the last one is, let's take x equals 0. Like I said, this is the favorite. So if you take x equals 0, the whole thing becomes 0, and this value becomes 6. Kind of coincident, like the thing the last time. So now anyhow, so the only thing left right now is for us to plot this on the graph. So why don't we go ahead and do that and see what we get. So here what you will now see is that when we try to, so let's do the same thing what we did. So we have 5 and 3, 10 and 0, and 0 and 6. So let's get our graph and let's get our table in here. So we have 5 and 3, 10 and 0, and we took x equals 0, we got y equals 6. So now, and this is our x-axis, x dash, y dash, and this is our origin. So all are positive values, so our graph will be basically in this area here, right? So let's plot the first point. So the first point is, I think we lost it, so let's write this again. So we have for 5, when we have x equals 5, we have this value as 2. Then when x equals 10, y is 0. When we take x equals 0, y actually is 6. Now let's plot each one of them one by one. So first, for x equals 5, 1, 2, 3, 4, 5, y is 2, 1, actually y was 3, y is 3, 1, 2, 3. So you can quickly take a look at that. So our polynomial was px equals minus 3 by 5 times x plus 6. So when we took x as 5 and 5 cancelled out. So 6 minus 3 is 3. This is not 2, this is actually 3. So the first point is x is 5, 1, 2, 3. This is our origin. 1, 2, 3, 4, 5. And y is 3, 1, 2, 3. So this is our first point. Our next point is over here, which is for x equals 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For x equals 10, the value of y is 0. So this is the point. And then finally, we have for x equals 0, y is 6. So 1, 2, 3, 4, 5, 6. And then we have joined the 3 points. So again, friends, here what we have seen is for this linear polynomial, px equals minus 3 by 5 x plus 6. What we are getting is we are getting a straight line. So now what you will see is that no matter what kind of linear polynomial you write, whenever you are trying to do a graphical representation of that particular polynomial, what you will see is that you will always get a straight line. That is the geometrical representation or a graphical representation of a linear polynomial. Is always a straight line. So whenever you take a linear polynomial, that is a variable with degree, a polynomial with degree 1, and if you draw it in the form of a graph, you will always get a straight line. Now recall that whenever you draw a straight line, you just need 2 points. To draw a straight line, you need 2 points. So why I have mentioned to take at least 3 points. So in both examples, we took at least 3 points. If you would have chosen, you could choose to get more points. It will just take longer, because for each of those points you have to find out the value of the polynomial, add those other values of x. The reason is that we know that you can draw a straight line with only 2 points, but we wanted to make sure that the third point that when you extend the straight line, that the straight line actually also goes through the third point. That is, at the minimum we need 2 points to draw a straight line. That's all we need. But by taking the third point, we are making sure that indeed all points on that polynomial, they fall in the straight line. And on a lighter note, as you can see clearly, just to draw a straight line like this, I have totally, made many attempts. That is the reason why I had actually picked those polynomials and drawn those graphs prior, so that we don't end up trying to draw them, and then the lines will look like all fancy curves. So I hope, friends, that you have realized that this is the first time we're looking at geometrical representation of a linear polynomial, and no matter what kind of linear polynomial you take, it will always be a straight line.